Okay, so welcome back. This is part 7 in our series where we're showing you how you can write your own hardware monitor application in C# Visual Studio. And it allows you to monitor things like voltages on your motherboard or your CPU temperatures, GPU temperatures, fan speeds, and that kind of thing. And we talked in previous videos how you can, of course, get a free application that does that. But you can also get a free and open source application that you can download and use with your C# or whatever application you develop. And here in the middle is one of those applications we talked about before. It's called Libre Hardware Monitor. And it's an application you can download and run, but you can also use it as a library reference, a NuGet package. If you're going to write a simple C# application or whatever, you can reference all the functionality in that to grab what you see here on the left. On our application, we're charting some values. And again, this is a free open source application. However, we also talked about some of the downsides of free and open source software. This Libre Hardware Monitor, the original code was called Open Hardware Monitor, and that died about 2020. And then there's been hundreds of forks of that. And one of the more popular ones is this Libre Hardware Monitor. Well, we talked about some of the negatives of free and open source software. And I encourage you to look at those previous videos where we talk about Libre Hardware Monitor, how to install it, and some of the downsides. And what we're trying to do is write our own code from scratch rather than relying on these libraries. We're trying to write our own code from scratch that does a custom version of this, because, a lot of people don't really need all of the stuff that is generated by these applications. We've got memory, we've got SSDs, we got all kinds of stuff that maybe you don't care about. So it'd be nice to be able to write your own application like you see here. You can customize it, you can chart it, you can compare certain values. So what we're showing you in this series is how to do that and ultimately get away from these open source libraries and do it yourself. Now, in the previous video, we talked about how to do that with our GPUs. Now, in this particular computer, I've got, as you can see here, 2 NVIDIA GeForce GPUs. And we showed you how to not use this library, but directly access using what are called APIs provided by NVIDIA, so you can access the data on their GPUs. We developed this application here that, in just a few lines of code, allows you to grab, in this case, the GPU temperature, and we're charting it on a scrolling chart in real time the last 10 minutes. And it was very easy. We didn't have to use this Libre Hardware Monitor or any other open source code to get it. We could get it directly from the NVIDIA code. So really nice way to customize it and make it a lot simpler and not have to rely on other people's code. So what we're going to do in this video is we're going to take the next step, and we're going to look at another component besides a GPU that gathers data, a data acquisition device, and figure out what it is, how it works, how we can communicate with it, and how we can grab data from it. And the device we're going to look at is called a Super I/O. Now, what is a Super I/O? Well, here as an example, we're running the Libre Hardware Monitor application we talked about previously. In our computer, it's got these different categories of devices. It's got our motherboard, our CPU, memory, and our GPUs, and then our storage media. And if I open up the motherboard, you can see there's a component under it, and it said is a Nuvoton NCT 6795D. That is a Super I/O. And we'll talk about the Super I/O in this video, what it does and how you can communicate with it. But you can see here that it is giving you data on various motherboard values and sensors. So for example, it's got voltages, V core, which is the core going to the CPU, the voltage 1.168, and this is real-time data. AVCC, the 3.3 rail, the standby, the CMOS battery voltage, 3.3 volts. And it also has 4 temperatures here from devices, I'm not sure what they are, but you can see it's got the real-time temperatures, and it's got a whole bunch of fan data. For example, it's got 5 or 6 fan speeds in RPM, and then it's got these fan controls where it tells you what the controls are set for these fans when they go on and off. So this Super I/O has a lot of information about motherboard related voltages, temperatures, fan speeds, and so on. So what we're going to do is we're going to look at this and we're going to see what data it's got and how we can communicate with it and write it in our code. So the first thing is, if we're going to look at a Super I/O, how do we find out what our Super I/O is? Well, again, if we run this Libre Hardware Monitor, it tells you that it's a Nuvoton NCT6795D. There are other hardware monitoring applications or hardware data applications that can also tell you that. Some of the more popular ones, HW Info, I don't think it tells you that. But here we've got CPU-Z, and if you look on the motherboard tab, it says the manufacturer, the model of the motherboard, the bus, and so on. And then down here it says LPC-IO, and it says Nuvoton NCT6795. So it's telling you the name of the Super I/O, and it says it's an LPC-IO. Keep that in mind. Remember the LPC. That means low pin count, and it gives you a hint about how we can communicate with that, because there's a thing called an LPC bus. So keep that in mind, but it tells you what the Super I/O is, and it gives you a hint about the communication. So now let's look into this particular Super I/O and try to understand what it's doing and how we communicate with it, and that will help us to understand Super I/Os in general and how we can deal with them. So Super I/O, here is a photo of a Nuvoton Super I/O, and this is an NCT6791. It's a little bit different from our version, but you can look on your motherboard to find out what the model is and what the manufacturer is. It's going to be a chip that looks kind of like a CPU. It's got a lot of pins on it, and typically the manufacturers are Nuvoton, which used to be Winbond. You may see Winbond chips on your board. Also ITE Tech, FinTech, and Microchip Technology. So if you want to look on your motherboard to see what the Super I/O is, you can look for chips with a lot of pins and with some of these names on it, and that can help you get the model number. So here is kind of a general layout of a Nuvoton Super I/O chip. This is from the Nuvoton website. And you can see it's got, over here on the right, it shows a bunch of monitoring like we showed. It's got voltage, temperature, and fan. And we saw that in the Libre Hardware Monitor where it's measuring voltage, temperature, and fan. Also, it's got other SM bus temperature sensors. We can talk about that later, and that's over I2C. You can see it also handles the old COM ports, the serial COM ports, LPT, which is the old line printers, and then PS2 mouse and keyboard. And you can see it's also got LPC. Again, we see this LPC communication with the CPU and chipset system on a chip. So we're starting to see that the Super I/O can do a lot of things. ACPI power sequence control, GPIO, and 7-segment LED. But here you can see that, yes, if you want to get some voltage, temperature, and fan data, you can access the Super I/O, and probably it's going to be over this LPC communications link. Now, when we talk about this LPC, keep in mind that there's an evolution of Super I/O communications over the years. It started out as an ISA bus long ago, and that kind of went to a PCI bus for the Super I/Os. But LPC bus is a newer Intel bus that has taken over, and the newest version, as of about 2016, is the ESPI bus. So there might be some confusion about Super I/O communications. We're going to focus on this LPC bus, which is what, as we'll see, our Super I/O mainly deals with, but keep in mind that can be different communications paths. Now here is another general graphic of the Super I/O and other components and how they deal with the CPU and the chipset. You can see there's a north bridge and a south bridge, the south bridge being the I/O controller hub. And you can see that the south bridge is kind of sort of like a Super I/O, where it communicates IDE, SATA, USB, Ethernet, audio codec, CMOS memory. and those are cables and ports leading off the board. But down here you've got the Super I/O that has serial port, parallel port, floppy disk, keyboard, and mouse with cables going off the board. And here it shows, yes, it goes LPC bus. Super I/O goes to the south bridge via an LPC bus. And over here you've got PCI slots for the PCI bus for your GPU and whatever, and that goes to the south bridge. And then you've got high-speed graphics bus, AGP or PCI Express, to the north bridge. And then you've got your memory slots. So we're starting to see that the Super I/O is one I/O chip that has a lot of functionality and probably communicates over this LPC bus. So if we're going to be dealing with the Super I/O, we're probably going to want to be familiar with this LPC bus. So now in a previous video in the series, we looked at this document here, which is the data sheet for the Nuvoton NCT 6796D. Now, as we showed, we've got a 6795D, but this is the closest I could find for that Super I/O. And it's a Nuvoton LPC/ESPI Super I/O. And now this is starting to make a little bit more sense to us. LPC is the communication path, and the newer version is the ESPI. And this is dated 2017. So we can take a look at this in more detail and hopefully understand a little bit better about how we can communicate and what registers we need to access. So if we scroll through here, we've got pin descriptions, and then we come down to section 8. It's called Hardware Monitor. So there's a whole section here based on the thing that we're concerned with. General description, access interfaces, and then it's got the LPC interface, the ESPI interface, and the I2C. So you can see that LPC interface is one that we're going to look at, but it's got other possible interfaces. And then it's talking about analog inputs. And of course, as we saw, if you're going to have voltages you're monitoring, or fan speeds, or temperatures, you're going to have some inputs. And then this is basically a data acquisition device. It's going to convert those through an analog to digital converter into a digital value that you're going to put into a register. So we've got the analog inputs, fan speed measurement and control, more fan stuff, alerts and interrupts. And then section 9 talks about the hardware monitor register set. As we said before, you're going to do an analog to digital conversion and put the results into some registers that you can access over the LPC communications link. So you've got a whole bunch of stuff, the aux fan out, temperature monitor, and if you're looking here, you can see banks. They're referencing banks, which means they're probably registers in different banks, bank 0, bank 1, and so on. So this starts to give us an idea of how we can start to reverse engineer this and find out, how we can communicate over LPC and what registers we can access. Now, another source of information, if we want to find out what is low pin count, in Wikipedia, it's got an article talks about low pin count. And here you can see created by Intel in 1998. It's been around for a long time. It was superseded by ESPI, which we mentioned in 2016. It's 4 bits in width with 33 megahertz. There's some history here. It tells you about the low pin count is a computer bus on IBM personal computers to connect low bandwidth devices to the CPU, such as the BIOS ROM, legacy I/O devices integrated into Super I/O, embedded controller, and so on. So this gives you kind of a background on LPC. And you can see down here there's an old WinBond LPC chip. And then if we scroll down here, you can look at the diagram we showed before and some of the data on it. So that kind of gives you a little bit of background on the LPC. Now you can also look at the Intel low pin count specification. This is from way back in 2002. This is the latest one I found. There may be later ones. And that can give you some more information about the LPC to find out how it works. And as we mentioned before, if we look at the Libre Hardware Monitor library code, it's this project here, Libre Hardware Monitor Lib, and you go under Hardware and then Motherboard, you'll see a folder called LPC. And under LPC, as you might expect, there is an LPC I/O and an LPC port. So indeed, there is some use of the LPC communications. So what we can do is we kind of use this as a guide to help us kind of reverse engineer one way to get to the Super I/O. And if you look in the lpcio.cs, there's a class LPCIO, and of course it mentions Super I/O, so it's getting all the Super I/Os to array, and then we've got code here to deal with those. So we can use that as some sort of a guide. Again, there's no documentation, so it might not be too useful, but at least we have that here, and we know that we're at least on the right path. So now the question becomes, how do we actually communicate with the Super I/O over this LPC and grab data from the registers? We've got a lot of background data. We can see from the data sheet what the registers are. The question is, how do we actually implement this and connect with the Super I/O? And to figure that out, one thing we can do is go back to the Libre Hardware Monitor library and see if we can figure out how they are doing it, and maybe that will give us some ideas. So I'm back in the Libre Hardware Monitor code that we cloned from GitHub. And again, it's got two projects. It's got Libre Hardware Monitor as the actual application. And we're in the library that you can access in your application. And you can see it's got a hardware folder under which it's got battery, controller, CPU, GPU, memory, motherboard. And if you open up the motherboard folder, you can see it's got LPC as a folder and a bunch of stuff under this LPC. So that might help us pinpoint where it is accessing the Super I/O over using LPC. So we look here, we've got a F718XX, which sounds like a model number for a FinTech Super I/O. We've got an IT879X. We've got two of those, which might be ITE, as we talked about before. We've got a W836XX, which is probably a WinBond. And right above it, we've got an NCT677X, which sounds like the model number of a Nuvoton Super I/O. We've got an NCT6795, not a 677X, but this is getting us pretty close. Maybe it's just they didn't update the class name or whatever. So let's see if we can look at the code in NCT677X and see if we can find something. So here's NCT677X. It inherits from the interface Super I/O. And you can see it's got a struct with temperature source data, a fan count register array, initial fan control mode, is Nuvoton vendor, max fan count, a lot of fan stuff, temperature source data. So it's got an array of temperature source data called temperature source, battery monitor, control register, voltage registers, and so on. So it sounds like we're getting really close here. So if we look, the constructor, you give it a chip, a revision, a port, and an LPC port, and presumably it can use that information to communicate with the Super I/O on that LPC port. So we've got a chip, we've got an array of controls, array of fans, array of temperatures, array of voltages, read GPIO, write GPIO, set control, update, get report. And here we've got a read byte method. You give it an address and it reads a byte and returns a byte. Aha! So if the chip is not chip NCT6683D, which ours isn't, or 6686, which ours isn't, or 6687, which ours isn't, then you go in here and you can see you've got a bank description. And we saw in the Super I/O data sheet that the registers are broken up into banks. Then we've got a register number. And then we have what looks like our actual reading and writing to the I/O port. And it says ring0.write I/O port. And you give it an address and an offset and a bank select register. And then you write again to the port, data register offset and bank. And then write again to the I/O port, address, register, offset, and register. And then you return what you have read. You read to the I/O port, port plus data register offset. And presumably that's the core of how you can grab data from your Super I/O. If you know the address and the bank, you can grab the data. Now, what is ring 0? Well, if we go into Wikipedia, we can find that ring 0 is a protection ring. And it says in computer science, hierarchical protection domains, often called protection rings, are mechanisms to protect data and functionality from faults by improving fault tolerance and malicious behavior by providing computer security. So computer operating systems provide different levels of access to resource, and you can see here ring 0 is a kernel with the most privileges, and it goes up to ring 3, which is the least privilege. And apparently, in order to get this data, you have to use this ring 0. And it says on most operating systems, ring 0 is the level with the most privileges and interacts most directly with the physical hardware, such as certain CPU functionality and I/O controllers. So now we are at the point where we have to decide if we want to deal with these security-related protection levels, and in particular this ring 0, which is the most privileged. And it's at this point I'm going to decide to pass on this because, first of all, it's not the right thing for a YouTube channel. I mean, I get no views here anyway, but to get into the depths of this, security stuff can be dangerous, and it's just a lot of work and probably not worth the effort. Nobody's going to watch it anyway. So if you want to go down that rabbit hole, good for you. I'm going to pass on this, and maybe if I do more videos in the series, we'll look at some of the other components and see if we can access them without going to this ring 0 level and getting involved in all that. Otherwise, that's about it for this discussion of the Super I/O and gathering data. Maybe, like I say, if we go to another video in the series, we might look at another component. Otherwise, that's it for this one. If you like any of these videos, I encourage you to hit the like button, subscribe, and hit the bell notifications. But most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.